All right. All right, so I believe everything is working. And welcome to the new semester. And just as usual, whenever you have any query during the class, feel free to ask them in the live chat. I'll make sure to answer your queries. Right? And we shall be waiting here for 2 more minutes and then we shall actually start. Hold on for a moment because I think my live chat is not refreshing automatically. Hold on. All right, so welcome back. And as you might already know that we are going to switch a few courses in your curriculum from traditional programming languages like MATLAB and Scilab to Python. Right? So currently, if you look at any charts which actually compare the popularity of programming languages, you will see Python is currently the #1 programming language in the world. Okay, both for scripting and also for general purpose computing. Okay, and as such, it is quite essential nowadays to have some knowledge of Python. And I personally thought that it would be better if we incorporate the knowledge of Python programming into a particular subject in our curriculum. That way, you would have a good understanding of the programming language itself, and we won't be bothering with some stupid applications like printing certain lines, printing a star, and all those stupid things that you actually learn in your standard C programming language classes, right? We are not going to do those kind of things, but instead we are going to apply our knowledge of Python programming that we're going to gather in this course, and we're going to apply those into typical electrical engineering problems. Very specifically here, we are going to apply our knowledge to control system engineering problems, right? And for that, we are going to learn the basics of Python first. Okay, but again, the name of the series that I'm putting here is Python for electrical engineers, but rather Python for engineers for the most part, right? So we are not talking about computer scientists, right? So for the most part, I shall be skipping some intricate details about the language. Instead, we are going to learn how to properly and efficiently apply the language or capability of the language for our practical purposes, right? So this is what we are going to do. And again, this preliminary class will go on for 5 lectures total. Okay, so that within those 5 lectures, it will these 5 lectures will actually make up something like a crash course on Python, right? And after that, we are going to directly apply our knowledge into practical scenarios related to strongly related to electrical engineering, right? And and for example, if I give you my background in Python, when I was in my 4th year, we had a seminar in my university. We had a seminar from a reputed company, and in that seminar they talked about Python, for example, and that is the that was in 2011, I think, and that was the first time I heard about Python, right? And in those days Python wasn't that popular, right? So again, I went back home and I thought, okay, right now I have pretty much spent my 3 years of undergraduate engineering, and now I have to learn a programming language. I need to learn a programming language so well that I can apply it anywhere I want, right? So I thought about that, and then somehow, due to, of course, popular opinion, I chose Java, for example. And when I started learning Java, you won't believe it. For example, after just 2 or 3 days, it felt so complicated that I left it completely. Then I looked into Python, and then I never came back. But because once you learn Python, the simplicity of the language, the efficiency of the language automatically draws you so much in that you cannot go back to other languages, other primitive languages. It is not to say that those other languages like C++, C, Java, they do not have any application. They do have their applications, but for most intents and purposes, Python would be one of the best choices that you might have, right? So, and I can without a doubt say that Python is the easiest programming language in the world. It is the easiest programming language in the world because it actually removes many complexities that are present in programming languages. Because the creator of Python, Guido van Rossum, while creating Python, his motto was very simple: make a language that is readable. So Python is designed in a way that that if you see a code written in Python, you can, even without knowing what is happening, or rather even without knowing the programming language itself that much, you can gather what is happening in the flow, right? Something like that. So Python is designed to be readable, and that will be evident quite shortly. Okay, and that was one of the mottos, for example. Okay, and for that, there are things Python sacrifices, and there are certain advantages that you get alongside that. And along with that, Python is a very easy language because there are certain intricacies with other languages that Python simply gets rid of. Okay, now of course, no good thing actually comes without a cost, right? You cannot if you gain something, you lose something. That's quite understandable, right? So while Python gains advantages in terms of how simple it is, how easy it is for beginners to learn, it gets a performance penalty. For example, if you write an efficient code in C, for example, okay, that might be somewhere around, say, for example, 10 times as fast as a comparable Python code, for example, right? I'm talking about pure Python. If you write something in pure Python, and if you write the same thing efficiently in C, you might get a 10 times performance boost in C, for example, right? But at the same time, what happens is the code that you're going to write in C is probably going to take you weeks if it took you hours in Python, right? So this is the point here. So you are actually trading computational time with development time. So with Python, you can develop something in a day, okay? And of course, what you develop with Python might be slower, but what you can develop in a day with Python, that might take you, say, for example, 7 to 10 days to develop in C, for example. Even if, provided that you can develop that in C, for example, right? So this is the idea here. The idea is that you are trading computational time with development time, right? So while using Python, Python is very good in terms of development time, right? So if you want to develop something quickly, Python is your best choice, right? But if you want to develop a code that has to be extremely efficient and all, Python might not be a good choice in that scenario, right? And same goes for JavaScript in the other hand, right? So there are so many things that Python is good at that often the disadvantages are quite negligible. And in case you want to develop very powerful and what should I say, efficient code in Python that runs very well, you might have to sacrifice some amount of your development time, and there are modules inside Python that actually can help you, or rather that actually does help you, would help you in developing a faster Python code. Okay, there are modules like Numba, 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 like Cython. Those can actually help you develop Python code that runs as fast as a native C program. So there is nothing, so this is basically a win-win situation, right? So if you learn Python, you can very quickly create a code that works for you and with a very minimal development time, right? But if you want an efficient code, then you can spend some more time on your Python code and develop it in a way, or rather modify or improve your code in a way that gives you improvement in runtime as well, right? So in that sense, Python is pretty much usable in every programming scenario. For example, one of the popular examples nowadays why Python took off recently so much is machine learning, and specifically deep learning. All the modern packages for deep learning like TensorFlow, Torch, this kind of all the modules that so AI, machine learning, this is the buzzword of 21st century, right? And all these buzzword technology, AI, machine learning, deep learning, all these packages have interfaces with Python. The primary development interface for TensorFlow, primary development interface for PyTorch, these are the deep learning modules used by Google and Facebook respectively, are done in Python, right? The interface is done in Python. So whenever you are developing a code in TensorFlow or code in PyTorch, you would be doing your code in Python, right? But under the hood, they are running C++. So it is best of both worlds, right? So you are getting the performance of C and C++ while you are getting the ease of use of Python that comes with Python, right? So that is why Python took off so much in the recent years, because of deep learning and machine learning, all these kind of things, where the interfacing language is basically Python. Under the hood, everything runs C or C++. Python itself, the Python compiler and Python interpreter, those themselves are written in C. So Python is popularly known as C Python in this particular scenario. But everything actually under the hood runs C and C++. So under those scenarios. So yes, so basically your choice of tools would determine whether or not your code actually runs fast. With that aside, let's talk about a very simple philosophy here. Very simple philosophy here. The idea is that you want to accomplish something, right? In your life, you might want to accomplish something, for example, right? So let's consider your accomplishment A. And this is a very simple understanding. You will see why I'm talking about this. So this is what you want to accomplish, right? For example, A is the amount of thing you want to accomplish with a programming language or with a tool, for example, right? Right. So, and this is the amount of thing you want to accomplish. Say, amount of thing right? All right. So, and for example, here is D. D is the difficulty. Okay. And T is the amount of time you need to accomplish something, right? So understandably, if you have a constant amount of thing, right? So for example, if you have a constant amount of thing that you want to achieve, understandably, and the tool that you are using to achieve that constant amount of thing is very difficult to use, then the time required would be larger. So the understanding is very simple. You want to develop something, right? And the tool that you are using to develop something is very difficult to use, right? So this is the thing, the amount of thing you want to develop, and this is the difficulty, right? right? And this determines the amount of time you need to develop something. Understandable, pretty understandable, right? So now if you have a constant amount of thing that you want to develop, then if you choose an easier tool, then of course the amount of time you would need, right, to develop that thing or to achieve your goal would be smaller. Or other way around, if you choose a tool that gives you less amount of difficulty, that has a less amount of difficulty associated with it, then given you have a constant amount of time in your life, you can achieve more with that, right? So if D is lower and T is a constant, then A will be higher, right? Understandably. So that is the idea here. So with Python, you can do easy things in a very easy fashion, and you can do complicated things without much of any hassle. That is the idea here. So without spending a huge amount of time, you can accomplish a good amount of things here, right? That's the idea, right? So Python, let's first, you might have heard about Python and might have been taught by different teachers. Let me get rid of one essential confusion. Okay, some people would tell you, unfortunately, this is quite unfortunately true. Okay, I have seen teachers teaching this way. Unfortunately, some people would tell you that Python is an interpreted language. Right? Some people would tell you that Python is an interpreted language. For example, you know that a compiled language, whenever you write something, you compile that code and a machine code is generated and that is run. And for an interpreted language, the language is executed line by line. Some people, some teachers specifically, would tell you that Python is an interpreted language. This is absolute garbage. Python is a compiled language. I'm telling you why. Okay, Python is not at all an interpreted language. If you have heard that from somewhere, they have taught you wrong. Anyway, so with that aside, keep that in mind. And let me tell you, I was under the same impression that Python was an interpreted language. Then later on, when I understood the internal behavior, then I realized that how wrong I was. All right. So first things first, let's discuss how we can actually run Python, right? So there are several ways in which you can actually run Python. So the first thing you could do, you could go to python.org, right? You can go to python, and again, if you have any query, feel free to ask here. Okay, the first thing you can do, you can go to python.org. Okay, here you can download Python compilers and everything. Okay, but this I wouldn't recommend to you. I mean, this is good for, for very beginners, right? But for the purposes that we are going to use Python for, this is not the suitable thing, right? So don't download Python from here, right? Do not download Python from here, right? Now let's do a Google search. Okay. And let's search for this, Anaconda. So this is the funniest thing. When I started learning Python, okay, when I searched Anaconda, the first result that would come out of a Google search is Anaconda the movie, right? And Anaconda the snake, right? But nowadays, when you search Anaconda, you would get the first Google search would be this one. Okay, so this is related to Python programming language, right? This is related to Python programming language. So that actually tells you how popular things have become, right? So Anaconda Python distribution is more popular than Anaconda movie and than Anaconda the snake, right? And yes, this is the same Python. Some of you are asking whether that is the same Python as this one. Yes, this is called a Python distribution. So the idea is that whenever as engineers we are using Python, for example, okay, whenever as engineers we are using Python, we use Python as the base. And based on, okay, someone is asking why is the name Python? Okay, there is a funny thing about that. Okay, let me just clear that up. The funny thing about that, the developer, the person who developed is Guido van Rossum. And Guido van Rossum is an awesome person, right? And Guido van Rossum, while developing Python in late 1980s, early 1990s, he used to watch a show called Monty Python and something, right? So Monty Python used to be a what should I say, comedy show back in the 90s, right? And he actually developed Python while and in his leisure time he used to watch Monty Python. Okay, Monty Python show basically. And so based on that, the name of the programming language is Python. It is not named after the reptile, if you are curious. So it is named after Monty Python. Yes. So it is named after Monty Python, the comedy show of 90s, which you probably not know about. Anyway, so the idea is that whenever as engineers we use Python, we do not use it as a standalone package, right? Because Python gives you many tools, but it also there are many things that we need on top of Python, so that actually we can develop our usual, what should I say, usual applications without much of any hassle, right? So with that said, on top of Python we require quite a few packages. For example, very specifically, we need packages for numerical computations, and for that we have a Python package called NumPy. Then we need Python for scientific computation, like solving differential equation, okay, doing integration, doing different types of computing different kinds of functions, doing probability and statistics, all those kind of things. Okay, so for those scientific computation, doing signal processing, doing control system engineering, for example, right, we need another package called SciPy, stands for scientific Python, right? So these are packages built on top of Python, but those do not come with the Python package that is offered at python.org. So if you download Python and install it from python.org, you won't get any of these packages, right? So NumPy, we have SciPy. Then of course, whenever you're doing computation, you might want to plot something, make a graph, right? So for that graphing purposes, you have a package called matplotlib, right? Understandable? Okay, right. So for example, we are going to do control system engineering. For our particular purposes, we would require a package called control, right? Okay, those who do image processing and they would need a package called image processing and generic computer vision. They would require a package called open computer vision, OpenCV. Okay, for example, those who do deep learning, they would probably require TensorFlow. Okay, things like that. But these do not come bundled with the base Python package, right? You understand what I'm saying, right? So if you download and install Python from python.org, you would just get Python, nothing else. Okay, but if you want all of these together, right? So if you want to develop something rather useful with Python, right? So you would require these and many other packages. Okay, but to install them manually might become a hassle, right? Some packages depend on something else, and that way there might be something called a dependency hell, right? So this package depends on this one depends on something else. So yes, you understand, installing one package might not be sufficient, right? And this is not a trivial process. Installing Python packages in a base Python environment is not a trivial task. Okay, things might become very complicated very soon, very quickly. So with that said, we have a concept of Python distribution. So what we essentially have Python distributions. So these Python distributions essentially packages Python along with many other useful packages, and they provide you with a useful way that you can use to install additional packages whenever you need, without jumping into dependency hells like that. Okay, so as engineers, we pretty much all engineers use Python distributions instead of standard basic Python, right? So that's the thing, right? Again, if you have any query, feel free to ask. All right, so let's go back. So if you make a Google search of this term Anaconda, the first website that you are going to encounter is Anaconda. Yeah. Actually, this company was established by the person who created the NumPy and SciPy package. And incidentally, he was an electrical engineer. I mean, he is an electrical engineer. Okay, he has a PhD in signal processing, for example. So you can understand the motivations behind all these things, right? So yes, actually electrical engineers have huge influence in computer science. Okay, right. So if you go to this website and go to product and then individual edition, right, and from there you can actually go to download, right, and you have 3 installers, for example, and unless you have a computer which is more than 10 years old, you are going to have a 64-bit computer. Okay, if you don't have a 64-bit computer, make sure to actually download the 32-bit installer, right? But it's very unlikely that you're going to have a 32-bit computer, right? So download any of these packages based on your operating system. Okay, I personally use Linux, so I of course download and install this one. Okay, and yeah. So if you're on Windows, download this one, install it. If you're on macOS, download this one and install it, right? So this comes bundled with many packages that are useful for us electrical engineers, right? But the problem is that often we don't really have a computer. Often we don't really. Sometimes we don't have access to a computer that's fast enough, right? That's fast enough. Or sometimes maybe we need to do some collaboration in some Python programs, right? Do you understand what I'm saying? Sometimes we need to collaborate with my colleagues on a certain Python program, right? So that might not be easy if I want to do it in my computer, right? If I am developing a program in my computer, I might need to get help from some other tools in order to collaborate with my colleagues, for example, right? Colleagues or friends, maybe, right? So just like that, you can have Microsoft Office in your computer installed, right? But in order to collaborate, so if you are making a document and you are doing it collaboratively, right? Maybe you want others to do some things as well, others to write something in the document as well. In that case, you probably would use Google Docs, right? In that case, you are probably going to use Google Docs, right? So similarly, Google has an application and it provides you actually for free. Hold on, yeah. It's called Google Collab. And I believe you people are already familiar with that from our signals and systems classes from earlier, right? So if you go to Google Collab, okay, so the website is collab.research.google.com. Okay, so that is the website here. So if you go to that website, and if you are doing that for the first time ever, it might ask you to accept some license, maybe, I don't know. Okay, so I've just pasted the link here in the live chat. So if you open Google Colab, okay, this will drop you to something called a Jupyter Notebook shell. Okay, this is a Jupyter Notebook shell, and this is one of the ways in which you can actually run Python, right? So one way would be to install Anaconda Python distribution, and from there you can run your Python code without any issue, right? Or in case you want to run your Python code in the cloud, and you want to collaborate with people, okay, you want to share documents. So if you use Google Colab, what you are essentially doing, you are working with Python programs in an environment that is very similar to Google Docs, right? And if you save a document here, it actually gets saved to Google Drive. And from that, from the Google Drive, you can actually share it with your friends and colleagues, okay? And you can collaborate on that, okay? Things like that, okay? So if you download something with a Python code, it actually gets saved to your Google Drive, for example, right? So here we have opened Google Colab, right? So I think most of you are following me on a computer right now. So I would request you to open the Google Colab link, and so that actually you can get started, right? So open the Google Colab link if possible, right? Because in the very first class, I would want some hands-on experience here, right? And I believe some of you already have this hands-on experience from our earlier classes on signals and systems. But I would urge you to, open this Google Colab link, right? And just so that you know, our control system laboratory would take place through Google Colab. So all the manuals will be provided to you as Google Colab notebooks. And you shall have to submit the assignments, submit the lab assignments and the laboratory works through Google Colab. So you don't have to do manual writing and scanning and sending, right? Okay, someone is asking, is there any app for Google Colab on Android? I'm not entirely sure. But I mean, doing a Python program in Android might not be the ideal. I mean, doing coding in your phone might not be ideal. I mean, if you have already code that you have written and you want to just execute that in a phone, that's fine. But typing in code in a phone might not be usual. Yes. So the thing is that once you open this up, go to File and create a new notebook. Go to File and create a new notebook. Okay. If it says filter notebooks, something, just try to open a new notebook. Okay, if someone has installed Anaconda, okay, in that case also, I would ask you to go to this one because there are certain advantages I'm telling you. Alright. 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 So you have, I hope you have opened that, right? And let's do that. Alright. Yeah, I just gave it a title because untitled is not a good title, right? Let me zoom in a bit so that you can see. All right. So now let me familiarize you with the interface here, right? So this is called the Jupyter Notebook interface. Actually, if you have installed Anaconda distribution, you can open the Anaconda prompt. Okay, on Windows you can open Anaconda prompt, and there you can write Jupyter space notebook. Jupyter notebook. Jupyter and notebook. So what you're going to get from that is the same thing in here. So this is basically Jupyter Notebook on the cloud with a few additional things. Additional bells and whistles from Google. Right. And this is a very powerful tool given to you for free. And I'm telling you why this is very powerful. You might not have a computer as powerful as the Google Colab platform that is being given to you for free. Alright. Alright. So if you have opened this up and if you have done that, of course you can see the Google Drive location and it says notebook stored in your Google Drive. So of course you understand I have stored everything in my Google Drive, right? Alright. So right off the bat you can see that there are two things here, code and text. So there are two types of blocks available in Google Colab. One is a code block, another is a text block, right? So if you click on a text block, what happens is you get a block where you can write something, right? Where you can write something. So you can write something, and if you click somewhere outside, okay, click outside maybe. So what happens? That appears as the text. That simply appears as the text. All right. So now I have this text. I mean, this is not a part of a code, right? So if you want to write something, maybe you want to make a documentation or something like that, you would select the text blocks, right? And these cells that has this kind of symbol, right? This kind of brackets as these symbols. These cells are the code cells, for example, right? Someone is saying codes are running like a PyCharm. So you might have said a term that actually is a valid term in Python community. PyCharm itself is an IDE. Okay, let me show you. All right. Maybe I cannot show you right now, but PyCharm itself is an IDE, Python IDE. So let me show you this. If you want to see that, right? It's again a Python IDE. It's a full-featured Python IDE. I personally use this one. Okay, but this is an advanced one. So unless you are an advanced Python user, don't use that. Don't even touch that. Okay, it would be completely overwhelmed. Anyway, so yes, with that said, let me delete this. Okay, all these cells that have this kind of symbol is a code cell, right? So let's start our very first Python program, right? Let's print hello world, right? Everyone does that, right? So this hello world example actually came from the Brian Kernighan's book, right? Congratulations on you. Congratulations to you because you use PyCharm, right? Someone is saying I use PyCharm, right? Hold on. Right. All right. So the first run would take a little bit of time, but look at here. Look at here. It says that you have a computer. I don't know whether it's okay. Just let me just hover over this one. It currently gave me a Google Compute Engine a backend with 12 gigabytes of RAM and 107 gigabyte of solid state storage, for example, right? All right, it gave me that. But alongside that, if you are doing machine learning and things like that, you can change the runtime type and select a GPU runtime. Okay, let me do that. And let me save that. And it is now saying allocating. What is happening here? It is giving me a computer, okay, Google Cloud Platform, for example, Google Cloud Engine Platform, where you have a GPU, and not just any GPU, a Tesla GPU. Okay, NVIDIA Tesla GPU, which is quite fast and powerful. Okay. Okay, now it says we have this. Let me just show you what computer we just got. Okay. Let me just see what kind of CPU we have. If Google shows us anyway. All right, so we have got an Intel Xeon processor, right? We have got an Intel Xeon processor. All right, and what kind of GPU have we got? Okay, we have got NVIDIA Tesla T4. Okay, we have gotten an NVIDIA Tesla T4 GPU. I'm not entirely sure, and it has 16 GB GPU RAM, right? 16 GB VRAM. So yes, we have gotten a very powerful computer at our disposal for free, right? For developing Python programs, right? You can understand what I'm talking about, right? All right. And if you need even more powerful runtime, for example, you can. So GPU stands for graphics processing unit, right? And TPU stands for TPU is specifically made by, created by Google. Okay, for doing deep learning computation, right? It's called tensor processing unit. So if you want even higher performance machine, in that case you can choose a TPU, but don't choose those things. Right now we are just doing very simple Python program. We are going to again change our runtime so that we have a simple computer without a GPU, right? We don't need a GPU right now, right? All right. Let me delete all these. All right. Let me run the hello world once again so that actually it initializes. Right. Happy. So very simple. Very first thing has been done. Right. We have our very basic Python program here. Right. But under the hood, it actually uses the Anaconda distribution. Something very close to the Anaconda distribution. Right. Something very close to the Anaconda distribution. Right. So whatever comes with the Anaconda distribution actually comes pre-built here, and also along with Google's packages here. All right. Right. So let's start our basic programming here, right? So again, Since I'm teaching you, I would probably write some additional textual information here along with my code. But again, anytime you have any query, feel free to ask. Again, I told you, Python is one of the the easiest programming language in the world, right? Since this is the easiest programming language in the world, things are self-explanatory most of the time, right? So intro. So I'm saying, so intro. All right. So I'm giving you the basics here. So this is how you declare a variable. You want an integer, so write x equal to 5. It is quite unlike C or Java or C++, where you have to declare the type of the variable before you can assign it a value, right? If it were C, C++ or Java, you might have to say int x equal to 5, right? Something like that. Okay, but that's not the case here, right? That's not the case here. And as such, Python is a dynamically typed language. Alright, Python is a dynamically typed language. A statically typed language would have variable names associated with a type. So whenever you declare a variable, you have to declare the data type first. Okay, so int x. So that defines x as a name that would store an integer, right? And later you cannot reassign x with certain other values, right? If you declare x as an int, if you say int x, you cannot assign it to a string, right? You cannot do that. Right? But Python is a dynamically typed language, and for that you do not have to, first of all, you do not have to declare the data type, and then secondly, you can assign a data of different type altogether to the same variable name. You get what I said? Let me show you what I said. All right, here I have x equal to 5. So presumably I have just assigned an integer value to the variable name x. And I believe all of you can see that, right? I have zoomed in 150% here. Okay, let me just print x. All right, so yeah, I have x as a variable and I have just printed that. Very simple, right? I think it's understandable, right? Not very difficult to understand, right? So x is an integer, right? So in case I want to see the data type particularly, so the function that I would call, need to call is the type function. So if I say type and then if I just write x, it shows me the data type of x and it says it's an integer. Of course, it's an integer, right? And just one more thing for attendance, please write down anything on the live chat. If you have your correct name in your Google account, otherwise just write down your ID. All right, so that's fine, right? So now what if I assign x with a string maybe? Okay, so maybe if I assign x with a string, and just one more thing, let me just make it a full screen, make it go full screen, right? So assign with a string, for example, right? All right, so something like that. So now x is now a string. So if I now say print x, I would say I would get this one, of course. Of course I would get this one, right? All right. So now let's see what is that type of the variable x. And just one more thing, how am I running this code? Of course, by clicking here. You can click here and that would actually run the code cell, right? Or whenever you are on a code cell, you can hit shift enter to run the code. Okay. You can either hit shift enter or you can hit control enter, or you can hit this, you can click on this play symbol here so that the code you have written would be executed there. So now we created a variable that was originally an integer, but then its type changed to a string, and this happened because it's a dynamically typed language. You did not have to declare the data type at any given point. Based on the value you have assigned to the variable, it has automatically determined the data type for you, right? So that is how Python is a dynamically typed programming language, right? Again, dynamic typing comes with disadvantage that you never have to declare the data type, but it has a disadvantage. it is slower than statically typed programming, a statically typed programming language. So if you have to declare the type, in that case, execution might be faster. All right. But before we go further, let me tell you how Python actually executes a program, right? How Python actually executes a program. Let me just clear that up. Okay. So usually you would write a code, right? The first thing you would probably write is a code, right? And of course, that's written in plain text, human readable text format, right? So you have written a code, right? And here what you're doing, you are just hitting the play button, right? For example, something like this. And that is executing the Python code automatically, right? But what is happening under the hood, it's a two-step process. It's a two-step process, right? So whenever you execute a Python code, two things are happening all at the same time. Let me show you what happens. The first thing that happens is a compilation. Okay. So whenever you execute a Python code, someone is saying in this case the variable counts will increase. No, what I said is that the variable x was reassigned to a different data, and its type was changed, but the variable count wasn't increased. All right, the variable number of variables wasn't increased. We have just a single name x in our namespace, and we can let me show you. Anytime you want to see the variables present in your workspace, just say whos and run enter. As you can see, we just have a single variable still, x, but x is now a string and its value is this one, right? So the number of variables did not increase. The previous value that I assigned, the integer that I assigned to x, has been discarded. Nothing else. So when you run a Python code, the first thing that happens is the compilation. And with that compilation, an intermediate code is generated, and this intermediate code that is generated is known as bytecode. So this is called Python bytecode. Okay. So when you run a Python program, what happens is first it undergoes compilation. So the code is compiled to an intermediate representation called Python bytecode. And this was deemed necessary, or rather the same thing happens when you execute a Java program. So whenever you execute a Java program, right, when you run a Java program, what happens is the javac command actually compiles the classes and everything into Java bytecode. Similarly, whenever you run a Python program, what happens is the code is compiled into Python bytecode. Now, what is bytecode? In future, I will be teaching you machine language and microprocessors and things, and as such, you would learn that, of course, you probably know it already, that computers, specifically the microprocessors that are there inside your computers, do not understand anything but zeros and ones, right? That's the common saying, right? Right? But the problem is, every single machine would understand those zeros and ones in different ways. Right? So if you have a computer that has a processor from Intel, okay, that would understand those zeros and ones differently than a computer or maybe a mobile phone that uses a processor from Qualcomm, maybe uses an ARM processor, for example, for that matter, right? So this machine code that we talk about, the code that computers understand by itself, the machine code, is different for different computer architectures, right? So if you have a different computer architecture, the machine code the computer understands would be different. Do you understand what I'm saying? So if I do my compilation directly to the machine code, for example, if I compile my C program actually compiles directly to machine code, right? But because of that, C program is not portable. So what I mean by that is, if I write a C program and compile it, what happens? I get a compilation or a binary for my computer, or rather for my particular architecture. You get the point? And this is not only machine dependent, but this is also operating system dependent, right? So if I give you a compiled Python code that I compiled on, compiled C code that I compiled on my Linux machine on a Intel architecture, Intel platform, you cannot run that on a Windows machine on an Intel platform. All right, you cannot run that on a Linux machine on ARM platform. You get the point. Since I have compiled my C program, if I compile my C program on a Linux platform, on Linux operating system and Intel platform, then that compiled code can only be run on compatible Linux platforms and x86 processors like Intel processors. If any of those conditions are violated, the code will not run. You have to recompile once more. So the codes written in C, C++, those languages are not portable. Okay? You compile it for your architecture. So if you want to support 10 different architectures, you have to compile it 10 different times, right? Because every different architecture understands the machine language in different ways. So that way, those languages are not portable. But that problem was solved first by Java. So Java was the first programming language, first portable programming language, and its tagline was write once, run everywhere. So Java's tagline was write once, run everywhere. So the motto was you can write it in a single computer, but the compilation would be done to an intermediate representation, namely a bytecode. A bytecode would be an intermediate representation that would be somehow understandable by all the machines, all the different machines, right? You get the point, right? So this is the idea here. The bytecode is an intermediate representation, but this is not machine language. The bytecode itself is not machine language. It's an intermediate representation, right? It's slightly above the machine language level, right? Machine language is just bare bone level. Basically, you can run machine language code directly on a microprocessor, right? Bytecode is slightly on at a higher level, right? But of course, a computer does not understand anything but machine language, right? But this is my computer. This is my microprocessor, to be very specific. For example, this is my microprocessor, right? Now this could be an Intel processor, this could be an ARM processor, this could be Spark processor, this could be PowerPC, right? This could be anything, x86, this could be RISC-V, any architecture. This could be any architecture, but this is my CPU where I want to run the code, right? But this supports a particular architecture, right? This understands machine language of a particular fashion, particular type. But in order to run that, you would need to convert this bytecode into a machine language code, right? You need to convert this bytecode into a machine language code, right? Understandable? So in order to do that, you have something called a Python virtual machine, Python VM. Okay, Python virtual machine. So what happens is the Python virtual machine would take this code from the Python bytecode that was generated by the compiler, and it will generate a code that is understandable by the particular CPU you are running the code on. And this process is interpretation, right? So do you understand what is happening here? So since you cannot, if you compile the code directly to the machine language, then if you want to support 10 different systems, you have to compile it 10 different times. But that problem is solved by Python and also by Java by compiling the code to an intermediate representation, okay, where you have something called a bytecode, and then bytecode is interpreted by the Python virtual machine to that particular CPU's machine language. So if you want to run this on ARM, for example, and on ARM, okay, the bytecode that will be generated by the Python virtual machine would be particular to the ARM architecture. If you want to run on x86, namely the Intel and AMD processors, the bytecode will be interpreted by the Python virtual machine for that particular architecture. So the machine code generated here would be for this particular architecture, right? So this is understood, right? So this is where interpretation works. So Python is a compiled language, I am saying, because the code itself is compiled. But after compilation, what you get, that thing is interpreted. But that's the job of the Python virtual machine. So whenever you install Python, any sort of Python, for example, what happens? You get a Python virtual machine built in with that. So you get a Python compiler and a Python virtual machine. So whenever you're running a code, that is first compiled to bytecode, and then the bytecode is being interpreted by the CPU. For Java, there is a small difference, just so that you know. There is a small difference for Java. Java actually also compiles the bytecode into the machine language code, but Python interprets the bytecode into machine language code. There are certain differences on that, but this is how a Python program actually runs under the hood. And that is why Python is also run once, write once, run everywhere. So you can run a Python program and run it everywhere with little to no modification whatsoever. That's not the same for C. I get the idea. So next time someone asks you, is Python a compiled language or a interpreted language? Your answer would be Python is a compiled language. Interpretation only happens between the bytecode and the machine language by virtue of the Python virtual machine. Okay. So any query up to this point? All right. All right. Nice. So, of course, I shall be teaching you many complicated things about Python, rather many useful things about Python. But the most important thing you need to remember is that Python supplies you with many high-level data structures. What I mean by that, the built-in array-like data structure that comes bundled with Python is called list. Okay, and those who are familiar with Java might be familiar with the term list. Okay, say I am defining X again, once again redefining X as an array, for example. Okay, and this array, I mean the array is a wrong nomenclature here, as a list. Okay, and the list would contain different values. Okay, the different values. So for example, say this list is containing certain, say for example, integers, maybe something like that, maybe -10 as well. All right. So I now have a list that has these values, right? So if I say print X, I get to see those values, right? So this is behaving like an array, right? So if you are familiar with C programming, I can say X0, and this gives me the 0th element of the array. So this is the 0th element of the array. So if I say X2, so this is 0th, this is first, this is the second element. So X2 would give me this. All right. So this gives me that. So understandably, so this is pretty similar to an array, right? But the power of Python comes in the way that this is a very high level data structure. This is a list that can support different data types. Okay. For example, if I say X equal to 2 and so for example 4.5, that's valid, right? So I have one integer and another floating point number here, right? But not just that, I can have a string. All right. So in the same array per se, right? In the same list, we are storing different data of different data types, right? We have stored one integer, we have stored one floating point number, we are storing one string. Then we can even store another list inside a list, right? Let's say another list. And this another list contains one string maybe, and maybe some integers, I don't know. All right. And then we can store a complex number maybe. We are engineers after all. 1 plus 2j. And you'd be happy with that term because we electrical engineers don't write I, we write j for the complex unity. And yeah, here it is. And we can happily print X as well. And if I run that, we have absolutely no issue. X is this one. Now this is something like an array, okay, or rather a list. that contains these different kinds of objects, right? So a list in Python has heterogeneous storage capacity, right? So it can store different types of elements, right? That's not true with Java, right? This term list is quite used in Java, but in Java you cannot have heterogeneous elements stored. One list would have a certain data type. So we have stored an integer object here, a floating point object here, a string object here, another list object here, and this list object itself contains one string object and one integer object and one complex number object here, right? But look at the indexing. So this is x0, so this is the 0th index. This is x1, this is the first index. Then this is x2, the second index, right? This is x3. So if I just say x3, if I want to see x3, this should return this one, right? If I say x3, this returns the third element from the list x. So this is the 0th element, first, second, and the third element. Third element itself is a list, right? So guess what I'm going to get if I say this. If I say something like this, x3, and again with second bracket, with brackets, I have 1. So what it does, it extracts the third element from x, which incidentally is a list, is another list, and from that it extracts the first element. So this is the 0th element of x3, and this is the first element of x3. So if I run this, I'll get this one, right? So this kind of indexing is also supported in Python. Right? So list is one of the very high level data structures that are available built in with Python. Again, without any hassle. I mean, creating a list and something like that in Python, in Java would be very difficult, right? Already, right? There are so many syntactical issues. But here it's very simple, plain and simple. Right? All right. So that is understood, I believe. Good. Right? Let's do a little bit of arithmetic, and let me show you again the power of Python here. Let us do some very simple arithmetic. So I can add two numbers. Very easy, right? No issues. I can add two complex numbers. One, say 1 plus 2j plus 2 plus 3j. Of course, it's a complex number, so complex number addition is taking place. I could multiply them. All right, I could do that easily. So I can take a number, okay, multiply it with another number. No issues whatsoever, right? I can take a number and raise it to a power. So now here in Python, this is different from other programming languages. Double star indicates power, right? So we have double star here. So this is power 2 raised to the power 8. So this is 2 to the power 8. So if I run this, this is 256, right? No issues whatsoever, right? Or what if I write something like this? A huge number raised to a huge power. Okay, someone is asking what is the data type of x right now. So we converted x to a list. The data type would be list. I'm showing you later on. Okay. So I have a huge number raised to a huge power, and let me tell you, you cannot do this in native C or C++ or Java unless you use something called the GNU multiprecision library, GNU multiprecision library, or GMP. Unless you use that, you cannot do this kind of computation, because the result is too large. As you can see, this number is too large to fit into any standard integer data types supported by C, C++, and Java. This is way too large, right? Can you understand how big this number is? Right? So this is huge, right? You can. So with Python, you can have infinite precision arithmetic, right? Yes, you can use math.pow, but there is a problem with math.pow. Right? Someone is saying you can, I mean, in C, if you use the math library, the pow, at pow we can use, at max you can use long double, right? Long doubles are, oh, someone is talking about Java, right? Someone is saying, can we do it math? Yes, but unfortunately what happens is, if you use math.pow, what happens is, you can only have doubles, right? Doubles, right? Doubles cannot store this long number, right? It will automatically interpret this with a mantis and exponent, and according to that, this would be combined to something to the power something and such, right? This much of precision will not be there. Do you get the point? This much of precision will not be there. That's the point here. Okay, this will be rounded off automatically to something into 10 to the power something. Okay. All right, so that's the point. So you can have multiple precision arithmetic here without any issue whatsoever, right? Not just that. Say, say for example, I can take a complex number and raise it to a power of 0.5. Can I do that? Yes, actually, we can. And what happens? We get a complex number as a result, right? So we have taken a square root. Okay, and you understand that, right? So 3 plus 4j, for example, that's a complex number. Question: can I raise a complex number to a complex power? Yes, also true. Who knows, maybe minus 3 plus 5j. So this is 3 plus 4j raised to the power of minus 3 plus 5j. Complex number raised to a complex power. Yes, Python does support that as well. So my point being, you can do very complicated things very easily in Python without any issue. So I can say minus 1, something like this. Let me show you. Minus 1 whole to the power 0.5. Right? So what do you get? You get something into 10 to the power minus 17. So 10 to the power minus 17 is so small that you can ignore it. And again, it is employing numerical methods, right? So you can forget this part because this is 10 to the power minus 17, so small. And the answer is 1j. 1j is your complex unity, right? So square root of minus 1 is complex unity, and you get that. Python actually can give you that. So again, it's pretty simple, right? So you can do very complicated arithmetic very easily here, right? Without much of any hassle. Okay, if you want to do complicated arithmetic like that in C, you would have to import a library called tgmaths. Okay, type generic mathematics, and then you can do some computation like that. All right. But that's not the only thing. Python, so this distribution actually comes with many libraries, right? So if I say conda list, oh sorry, it should be conda list. Sorry, hold on, with an exclamation sign. Okay, let me hold on. Oh, sorry. All right. So what I now have here, it's a very long list of things. What things? These are the packages that are pre-installed in Google Collab environment. So whenever you are using Google Collab, these are the packages that come pre-installed. That are pre-installed. There are so many packages pre-installed here. As you can see, I mean, there are so many packages, right? All right. So, I mean, of course, understandably, they offer many different things that you can do pretty easily, right? All right. Oh, I think this is pretty understandable, right? All right. So, in the next few classes, we shall discuss about the capabilities of Python in a canonical way. So, we shall talk about how different things really work, okay, and how different parts of the programming language would come together, right? But let me show you the power of Python in a very small and useful way, right? So oh, someone is asking if I can do this in Anaconda as well. Let me show you. So those who have installed Anaconda and want to do it locally, let me show you how we can actually do that. So for me, I have in my computer, let me show you. So this is a Linux computer, right? And here things would be slightly different from your typical Windows installation. So if you have installed Anaconda in Windows, go to the start menu, you would find something called Anaconda prompt. Open Anaconda prompt and write this. Write this. Open Anaconda prompt and write Jupyter Notebook. So if you have installed Anaconda, right? So do that. And if you hit enter, it would create a local server. So it would create a local server. What happened here? It created a local server. And you can see the link here says localhost, right? So it would create a local server and it will serve you the same platform or a very similar platform that is being used by Google Collab. So here you can do new and create a Python 3 notebook, for example. And can you see, this is very similar to the Google Collab environment that we have been using so far, right? So that is the only difference. So you have to open the Anaconda prompt on Windows, or on if you're on Linux or Mac, you can just open the terminal and execute this. Okay. And from there, you can go in your merry way doing the same thing. But only difference is that these things will be stored in your own computer. The runtime will be the capability of your personal computer here. The collaboration capability will be limited, and we shall not be using this for our classes. These are the differences. Other than that, if you want to program locally, this is really useful. I think this is understood, right? And once you are done, you can click log out here and say leave page. Okay. And go to the notebook and hit Ctrl C. And it will shut down the server that you just locally created, right? So that is how you do the same thing through Anaconda. All right. So I believe, so you got the same environment, you get the same environment. Right. But if you install Anaconda locally, there is an advantage particularly. You can use any IDE you want, right? I personally sometimes use Spider, for example. Let me show you again. So if you install Anaconda, Spider will come installed with it. All right. So I personally use Spider, for example, sometimes. Okay. And if I use Spider, so Spider gives you an environment that is pretty similar to the environment that you get with MATLAB. So those who are familiar with MATLAB would feel right at home if they use MATLAB, if they use Spider, right? So Spider stands for Scientific Python Development Environment. So this is one of the things that you get. So you can do the same thing with the same Anaconda environment that you could use otherwise. You could also use PyCharm, which I personally use. Okay, so these are the things that you could use other than the Jupyter Notebook environment, right? All right. So all these packages can help you do many different things, many different things. Okay, but let me show you some very useful things that you can do. Yeah, the thing is, someone is saying Anaconda, Python, Spider, what's left? Oh no, the spelling of Spider is SPYDER. Huh? Scientific Python Development Environment. Right. The naming scheme in Python is pretty funny often, because the original name came from a comedy show, right? And throughout the programming language, there are plenty of Easter eggs, so-called, related to those early shows back in the day, right? So let me show you how to import packages, right? So these built-in packages and many other built-in libraries can be imported with a simple import command. So if I say import and say math, so I have the mathematics package at my fingertips right now. So once I've imported the math package, I have the mathematics capability, or the basic mathematics capability in my fingertips. So I can say math.factorial, say for example, and I can compute the factorial of this number, maybe, who knows. And this is a huge number. Write down a program for computing the factorial of a number in C, maybe in Java. Use a long double, and you would only be able to calculate the factorial of, say, 32, not more than that. Beyond that, things will be rounded off. And here you have such a large number without any issue, and it computed it instantly, right? Instantaneously, so without any issue. So we have so many functions, right? And one important thing here, if you say math dot and hold on for a bit, okay, because everything is happening through Google Cloud here, right? So it will take some time. It will show you all the functions or methods, built-in capabilities that are there inside the math module, right? As you can see, there are so many functions that are already there in the math module, right? So whenever you want to call something from the math module, we would say import math first, and then math dot, okay, math dot, and then you can just write down whatever you want there, right? But sometimes what happens, the name of the package is so large, we want to give it a nickname, right? Just like we all people have nicknames, right? So for example, if I want to import the numerical Python package, which is NumPy, so I would say import NumPy, okay. But if I do that, every time I use something from the NumPy package, I would have to call NumPy dot, right? NumPy dot. So that NumPy is a 5-letter word, right? That might not be much useful, right? So we would give it a nickname, right? So import NumPy as NP. So that would be a short name for NumPy. So NP would mean the same thing as NumPy, right? So this is one of the ways in which you actually import packages. So you import a package as something, and if you write import NumPy as NP, that would indicate I have just given NumPy a nickname NP, okay? So of course the nicknames are kept short, right? So if you have a big name, your nickname is supposed to be shorter, right? So that people can easily call you. Your nickname is not supposed to be larger than your actual name, right? That's not the norm. And again, as far as standard practices go, many popular packages have standard nicknames. For example, NumPy has a standard nickname NP. So SciPy has a standard nickname SP, right? You are not supposed to give it a new nickname if you want others to understand your code, right? So every time somebody sees NP, and someone who is well versed in Python programming would immediately understand that you are talking about the NumPy package, right? So you can import NumPy, right, like that. So if you want some plotting capability, maybe you want to plot something, right? And the plotting capability would come from matplotlib library. Moments ago I told you already, right? So the plotting capability would come from the matplotlib library. So with that, I can import. Okay, and it's giving me already giving me hints, right? So from the matplotlib library, we have a certain package inside the matplotlib library. So matplotlib is a library, and from that we have a pyplot module, and we are actually importing the pyplot module from the matplotlib package as PLT. This is again a standard nomenclature here, okay, as a standard nickname. You're not supposed to create new nicknames, but you can write something like this. No one can really bother you. The code will run, but this is not the standard way, okay? So once you import things like that, what happens? You can run this, and now in your namespace you have NumPy and you have matplotlib, or rather, let me just call it PLT, right? All right, so we have NumPy and matplotlib imported here, right? Now, the moment I do that, I have the entire power of NumPy and matplotlib at my fingertips here. I can do anything with those packages, for example, right? I can do any computation with those packages. So let me show you a very simple example here. maybe I want to plot something, maybe, right? So if I want to plot something, say for example, I would create an array first, x, for example, and this would be a numpy array. Okay, and you have seen this kind of code, right? So we are going to create a linear space starting from 0, maybe ending at 10, and we shall assume 1000 points. So we have created an array that starts at 0, ends at 10, and we have 1000 points total, right? So we have created an array of 1000 points, okay? And we can say y equal to np.sign x. Do you see what is happening here? So understandably, we now have x and y. These are two arrays, and all those two things came from, both of them came from the NumPy library. From the NumPy library, we created a linear space that starts from 0 and ends at 100, ends at 10 with 1000 points. Okay, so it's an array basically. Okay, and then we have created another array y. All right, this would also have 1000 points, because for every point in x we are calculating the sign of that, right? Computing that, and I can now plot them. I can say plot x comma y, but unfortunately this plot function would actually come from the matplotlib library. So I would say plt.plot. So this linear space came from NumPy, this sign also came from NumPy, and this plot came from plt. And as such, if I run this, I have a plot of a simple sine wave, right? So that is easily understandable, I believe. All right. What are points? Someone is saying, what are points, sir? I don't understand. What are points? Can you just clarify your question so that I can clarify my answer? These dots indicate that we are calling a function from inside this library. So we are saying numpy dot means we are calling this linspace function from inside the NumPy library, right? So this dot indicates that we are calling the sign function from inside the NumPy library. Similarly, this dot here indicates that we are calling the plot function from the plt library. But what is plt? Plt is this module pyplot inside the matplotlib library. So it is like calling matplotlib.pyplot.plot, something like that. All right. Right. So whenever you, now this is one of the things, right? Okay. All right. Let me show you a few examples. Okay, let me hold on. Okay, someone's saying those 100,000 points mean. Let me just show you the variables we have currently in my workspace. Currently in my workspace, I have plenty of variables. I have the math module, I have the NumPy module, as you can see. I imported NumPy module. I have the PLT module, and this was mistakenly done by me. Okay, I have x which is a NumPy array. Okay, it's called an n-dimensional array. So I said 1000 points, right? So if I just print x, you would see what I mean immediately. If I say print x, do you see what happened? Those 1000 points actually mean that starting from 0 and ending at 10, I have divided the whole thing in such a way that I have a total of 1000 points. So first is 0, then I have taken 0.0 this point and whatever as such. So this array is automatically increasing and going up to 10 in small steps, such that we have 1000 points. That is why we have 1000 points, right? All right. Now, in addition to this, if you have Python installed in your computer, you would have additional capabilities, right? So this is working as a web application, something like that on the cloud. So it cannot access resources in your own computer. But if you want to access resources in your own computer, you might have to use standard Anaconda installation, right? So let me turn off my webcam here. Let me, hold on. If it would let me, I don't know. Okay, hold on. So what is happening is OBS is actually taking up my webcam here. So hold on for a moment. I am going to turn off the webcam for a moment so that I can actually run this code. All right. I believe that's fine, right? Wow, unfortunately, it seems like I cannot show you this one. Okay, this was a fantastic example in my collection, right? I could not show you right now. Anyway, because OBS is taking up my webcam here, right? Hold on, maybe if I mute the audio as well. Hold on. Nope, I cannot show you this example, unfortunately, because OBS is taking up the webcam, no matter what I do. All right. So what I wanted to show you was that Python has a capability of accessing your internal hardware. Okay, all the hardware you have in your computer, like webcams, audio interfaces, and everything, right? All right. So this is one of the very simple examples, right? We actually plotted a simple function here, right? If you want to do complicated computations, right? Complicated computations where the things are not numerical in nature. So far, what I have shown you is numerical in nature. By that I mean is that the functions that we are computing, they have numbers associated with them, right? Numbers associated with them. But if you are just a student, maybe a school student, and if I ask you what is the derivative of sine x, would you ask me that, okay sir, at what point do you want me to calculate the derivative? No. If I ask you what is the derivative of sine x with respect to x, you would tell me it is cos x, right? You won't ask me for the point at which you want to calculate the derivative, right? That is the idea, because sine x is a symbolic representation for you, right? But in many computations, we need symbolic representations for things, right? We do not need to compute things numerically. So far, what I have shown you is computation that are done through numerical methods. Now I'm going to show you Python's capability for doing symbolic computations where sine x is not treated as an array or a set of numbers, but it is treated as a symbol, so that if I differentiate sine x, I would get cos x, not some value at certain point, not some array, for example, right? And for that, I would import a package called sympy. So if I do that, so I am importing sympy as sy, right? Maybe I would just import everything from sympy. So if I want to import everything, it's a wildcard symbol, star. So if I import sympy as star, it will import everything from sympy. Yeah, sympy stands for symbolic Python. Okay, sympy stands for symbolic Python. So it is now going to compute things. We shall be now able to compute things symbolically instead of numerically. I'm just importing everything. This is again not recommended to import everything. but I'm just doing it for the sake of demonstration here. Okay, hold on. So this is the correct syntax, right? So I am importing everything from SymPy, right? So if I want to import a particular module from a package, I say from, for example, if I want to import linspace from NumPy, I would say from NumPy import linspace. I can do that. Okay? Understand? You understand that, right? Similarly, if I want to import everything from NumPy, okay, so I can say from NumPy import star. Star is everything. So I'm saying from SymPy import everything. From sympy.abc import everything. So this will give me the functions from SymPy, and this will make sure that all the variables that I declare now are symbolic variables. But again, this is for the purpose of demonstration, but this works right now. All right, right? So some of you might be might have some unhappy experience with your integrations, maybe, right? Maybe let's do an integral, right? Let's integrate maybe sin x. That would be very simple. Sin x with respect to x. So let me just run that. So as you can see, it did not ask me for a particular point at which I want to calculate the integral of sin x, right? It just gave me the value without any issue, right? I can say I can integrate maybe sin cube x. What is the integral of sin cube x? You have to do some factorization and something like that. So this is the result. This is the result. Okay. And one more important thing here. Let me just show you the power of this. Let me just check one thing. Okay. Is it even? Does it even work here? All right. Let me show you. It seems, oh, right, it works now. Okay, if I say init printing, what happens? You now have a rendered equation. So the integral of sin cube x is 1/3 cos cube x minus cos x. Fantastic. I wanted that. That is why I did init printing here. So it now actually prints things like that. So, right? Some of you might have had some bad memories of maybe Laplace transform. Let's do Laplace transform. Maybe sin x, maybe sin t, right? From t and s. So what are we doing here? What are we saying here? We're saying we are calculating the Laplace transform of sin t with respect to t. Okay, and the frequency domain variable is s. And we shall actually need those things in our control system classes, right? Laplace transform will be pretty much needed. If I do that, it gives me some weird thing, but let me just write down one more thing. And we shall explain all those things to you. If I now run this, of course, those, can you see this? Maybe it did not render properly, right? Okay, unfortunately, it did not render properly. That's quite unfortunate. But can you see it? There is a tiny 1/1 plus. Hold on. I cannot put up with this. Let me do that. Let me do that in my own computer. Google Collab is not somehow not rendering things properly, right? So let me do that here. All right. So now, say I want to integrate. So I want to calculate the Laplace transform. Let me just copy paste this. Where was it? Yeah, sure. All right. No, it actually is slightly bigger than the previous one. All right. So now it says the result is 1 by s plus 1 by s square plus 1. Very simple. Okay. What would you think the Laplace transform of sine 80 is? Of course, you know that, right? I believe a by s square plus sine square, s square, right? So you understand that. So let's compute the Laplace transform of t into sine 80. You can understand that, right? And you can even do something like this. You can say omega t, right? If you say omega t, it will understand you are talking about that omega, and it will write it as omega. So we are calculating the Laplace transform of t sine omega t. Maybe I want the Laplace transform of t square into sine omega t. So this is t square into sine omega t, right? That's the result. So this is very fast, really. I mean, maybe you might think right now that if you had this tool when you are in your third semester or maybe something like that, it could have been very useful, very helpful for you, right? Yes. Very simple, right? I believe. Similarly, you can do inverse Laplace transform. Yeah, you can do inverse Laplace transform. Maybe I want to do the inverse Laplace transform of 1 by s plus 1 from up to t. Right? So it says e to the power minus t into theta t, and this theta is the Heaviside theta function, which is ut for our purposes, right? So inverse Laplace transform of 1 by s plus 1 is e to the power minus t ut. So of course mathematicians do write theta t instead of ut. It's called the Heaviside theta function. The unit step is known as Heaviside theta function, right? So I believe you are getting this, right? So now we are not treating variables as numbers. We are treating variables as symbols, right? We are treating variables as symbols. So if I say type x, what is the data type of x? The data type of x is a symbol. It's a symbol. It's not a variable like an integer or a float or something like that. Right, something like that. So now you have this symbolic capability as well. So, and most important thing that you need to take away from this is that all of these things you are getting for free. You don't have to pay anybody anything to do, use these capabilities of the programming language. You're not installing any pirated software at all. And also these software licenses are giving you complete freedom. So you can take this code and do whatever you want, literally. Okay, all these things are open source. So you can download their source code and do whatever you want with them. If you know what we are doing anyway. Okay, right? So that way, it's really, really useful, right? So you understand what I'm saying, right? Okay, and you say Fourier transform. Okay, it will make me write it. What happened? Dirac delta? Yeah, Dirac delta t. Okay, so I'm calculating the Fourier transform of Dirac delta t. Of course, that's one. So Dirac delta is the unit impulse, right? So you understand the capability here. Okay, so right. So I believe, this is not a difficult thing to understand, that this actually gives you huge, rather immense power. For example, using these, you can do things that you won't even think about otherwise. For example, I can now integrate things like this. Sine x, maybe whole to the power 20, who knows. So now it immediately gave me the answer. Whether or not it is useful, that's a matter of discussion. That's a later discussion you can do later on. But just to show you the power of the things that we have built in here. So that is why, so understandably, if we just install Python, the very basic Python, we would not have these capabilities, because this came from a package called SymPy, symbolic Python. But here, if you install Anaconda or if you use it on Google Collab, you have these capabilities built in, right? If you have these capabilities built in, right? Let me show you one of my favorite things and my research area, say image processing. Say To do image processing, we import. Let me just restart the runtime. Huh? So whenever you have done this kind of, so this is a bad manner, okay, in terms of programming language. This is considered bad manner, okay. So if you do programming in a bad manner, you might have to restart your kernel once you want to write code in a good manner, right? So if I want to do that, so maybe I want to do image processing, for example. So I want to do image processing, for example, right? So I would import the image processing package. Okay, the package that lets me process images, for example, right? For example. All right. So let me just show you that. So just I'm going to end with this discussion because I'm going to I'm trying to show you that it is useful in pretty much every application area that you might want to think. Okay, that you can think about really. All right. So for that, I particularly would import. Maybe say for example, I would say from okay. So schimage is the image, one of the image processing packages available in Python. It's called scikit image. Okay, I just imported that, and from matplotlib.pyplot. Okay, rather I would say so. You have seen this, right? So I have run this particularly. So I would now create an image, for example. I would just pull an image from the sample data set. Data dot. Okay, I would. Now I have just created an array, and let me show you this for plt dot. So I have, right, Chelsea is a cat, for example. Okay, so now I have a cat image, for example, right? My favorite animal, right? So I have a cat here, right? So now, of course, some you know already that an image is made up of three color channels. Color image is made up of three color channels, right? Red, green, and blue, right? What if I want to extract the red channel particularly from this? Okay. Now we can use certain array slicing techniques from this, and I can say, for example, I want to see all the elements, all the rows and all the columns from the red channel, which is the 0th channel, and I shall talk about how you can actually how these things really work. Okay, and let me just show you. Hold on a second. CMap. So this is the red channel, but again, individual image color channels are separately grayscale channels, right? Black and white channels, for example. So now this is the red channel from the image, and if I run this, this is the green portion of the image, and this is the blue portion of the image. Of course, you can understand the blue portions are darker because very simply the image was reddish, right, in nature, something like that. So a very simple example, really, right? So Python can help you do many different things very easily. Okay. So let me end with a very simple example here. I don't know whether I have shown this to you earlier or not, but actually this kind of things actually really intrigue me. Okay, this was done by Barnsley, one mathematician in early 1990s or 1980s maybe, I think. Okay, and this is a very simple Python code, right? It takes maybe, it's around 30 lines of Python program, 30 lines of Python code here. Very simple Python code, 30 lines maybe, not more than that. Okay, so what is it doing? It's actually generating random numbers, and based on whether the random numbers are larger or smaller than certain values, it is assigning it a coordinate, right? Something like that. Let me run the program. Very simple Python program, for example, again. And what you have is a very nice looking fern here. Can you see that? This is known as Barnsley fern. Barnsley fern. Okay, you can just do a Wikipedia search on this. It is very intriguing, right? So as you can see, it's a self-similar fern. So the whole fern is similar to each leaflet here. The whole leaf is similar to the leaflets. So whole leaf itself is similar to the leaflet. Think about a single leaflet here, and also the leaflets are similar to the sub-leaflets here, and they are also self-similar. So this is called a fractal. Okay, and this is a wonderful domain of mathematics and control engineering. So this kind of some complicated things can be done so easily in Python, for example, right? Right. And just one more thing before we end our discussion here. Python supports Unicode. What do I mean by Unicode? This. Python supports Unicode, and by that I mean you can use Python with any natural language. By that, for example, I can write Bengali very easily in my computer. Okay. Right. So now I have just written Bengali in Python, right? So this is again a string. If I say whose, oh wait a second. If I say whose, now x is a string. Now whose value is a Bengali string, right? So x is a string. So if I say print x, now it prints a Bengali string, right? You can write any language in Python without any hassle at all, right? You can assign any language strings in Python variables, right? And as such, let me show you this. This is a Python program where even the variable names are written in Bengali. Okay, I created just as a demonstration of the Python's Unicode processing capability. Even the variable names, if you can read Bengali, you would be able to read that this is Bengali ko, this is Bengali ko, and even the variable function names. The name of the function is Fibonacci, for example. You can understand I am generating Fibonacci numbers here, right? I'm generating Fibonacci numbers here. So name of the function itself is in Bengali, and name of the variables are in Bengali, and everything. Let me just run this. It ran successfully, and it gave me the first 100 Fibonacci numbers, as you can see. Right? It's very simple, right? So these are some of the capabilities that you get with Python, right? These are hardly available in other programming languages. All right. So that will be the end of today's class, and today's class was mostly like a demonstration of what Python can do. This is hardly scratching the surface. Let me just show you a few more examples from, hold on. What am I doing? Okay, so just one example. Okay, so again, this is a gallery of the different types of plots that you can actually generate using Python. Can you see? It's a huge list of different types of plots you can generate using Python. So there are so many things that you can do with Python. Okay. So you have all the machine learning capabilities and everything that are built in with Python. Okay. And all the demos that I used to show you, right, were also done in Python, right? All the demos that I used to show you were done in Python. So you can understand the capability of this programming language, right? So for the next time, we are going to dive deeper into the programming language. We are going to learn certain canonical things about the programming language itself. And right. So in the meantime, I would request you to go to Google Collab or download and install Anaconda and try out a few things. Okay. And in case you encounter any issue, feel free to let me know. All right. So with that said, that will be the end of today's discussion here. Tomorrow we shall have a class on control system theory. And apart from that, that will be the end of today's discussion. If you have any query, feel free to ask right now. Otherwise, I would again encourage you to download Anaconda or download and install Anaconda locally in your computer or use Google Collab. But our laboratory classes will take place through Google Collab. Okay, keep that in mind. And just play with those tools for the week, I would say. And if you have any query, feel free to ask. I will definitely answer your queries without any issue. Right. So if you have any query right now, you can ask. Otherwise, we're going to end our discussion today. I hope you enjoyed the class, and we shall continue this kind of discussion from the next class. Right? All right. So thank you all for being here and patiently listening to me. And we're going to end our discussion right now. All right. Thank you very much. Again, if you have any query, feel free to mail me.